Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome my colleague from the Netherlands, BRAM MESLAND, who will tell us everything and more about curvature for differentiable Hilbert modules. BRAM, the internet, the Zoom, the floor, the screen is yours. Take it away.
Thank you very much, and very happy to be on this seminar again. I don't remember when the last time was, but it was sometime in the past 2 years. I'm going to indeed talk about curvature for differentiable Hilbert modules. I gave an experimental version of this talk in Krakow some weeks ago.
Yes.
Where I learned that giving Blackboard talks is terribly out of fashion these days. I was the only speaker on that physical conference that gave a Blackboard talk. So this was the opportunity for me to make some slides. And yeah, let me just get started. So this is based on joint work with Adam Rennie and Walter van Zuilenkom, which is already published by now in advances. Although the preprint is quite a bit older. It appeared right before the pandemic as a preprint. It's the first version. But then the pandemic made that I never really talked about this work. So that's what's going on now. Okay, so let me first set the stage a bit for the type of curvature we're going to be discussing in this talk. So curvature, as is known to, I think, many non-commutative geometers, links geometry to topology, and the most poignant setup where this happens is in the Chern character via the Chern-Weil construction. So let me discuss that briefly with you. The input for this construction is a differential graded algebra omega star d. So maybe I should use my no, I want to get the pen again, but can't get it to appear. There it is. Sorry about that. Just for you to keep track of where I am, more or less. So the input is a differential graded algebra, omega star d over a fixed complex star algebra A, say. And I'm not assuming anything about this A, it's just some algebra over the complex numbers. And that's what it will remain actually throughout my talk. So later on, some C-star algebras and so on will appear, but this curly A will always denote some fixed complex algebra that we have fixed from the start. And then a differential graded algebra is some graded object where the zeroth part is just A, and there is an operator on this differential graded algebra of degree 1, and it squares to 0. Okay, this is a very common object in mathematics. And the curvature we're going to be discussing today is the curvature of modules. So here X denotes, and again for the moment, an algebraic right module over A, and will remain to denote so in the rest of the talk. And on this module, we consider a right connection. So that's a map here in the middle from X to X tensored with the first part of our differential graded algebra, and the tensor product should be balanced over A. And then the connection should satisfy this Leibniz rule that I've written out relative to the differential. And then again, it's well known by an algebraic construction that we can extend this then to a degree 1 map on the tensor product of X with the differential graded algebra, as is written over here. So that's a map that's an endomorphism of X tensor omega of degree 1. And so we can, nothing prevents us from applying that twice. And that's how in algebra, the curvature of connections arises. So the lemma here says that if we apply this, this connection 2 times, we get a degree 2 map, but that map turns out to be alinear. Elementary computation will convince you of that. And it will be given by multiplication by a fixed 2 form, by which I mean an element of X tensor omega 2. And that element we call the curvature. I will usually remain to denote that just by nabla squared because it determines the entire map. Okay, so that's the setup here. And now the input here, let's go back to this slide with all the lines on it. The input here is one of these differential graded algebras. So the next question is, well, there are 2 inputs here. No, the first one is that, and the second one is the connection. But can we always get such an algebra? Well, again, if we restrict ourselves to pure algebra, then we can do this. We can just build a universal object, which is described on this slide here, where we start from the multiplication map on our algebra. That's structural data, right? And we look at its kernel. The kernel is a bimodule, and that is the bimodule of universal 1 forms. And then we just define the higher degree parts. Is there a question?
No, I don't see any question.
No, I heard some sound. So the nth degree parts are just the tensor product of this omega 1 with itself balanced over A. And then the derivation written here, the script of the straight D that sends one tensor A, that sends A to 1 tensor A minus A tensor 1. That is the first part of the differential graded algebra. And then you show that any element in omega 1 can be written in the way I indicate over here. So it's always of the form of sums of ADB type elements, and that allows you to extend the differential to higher degrees as well.
Sorry, Bram, there is a question on chat. It goes without saying A here is non-unitary, right?
No, I will actually make my life easy today, and I will assume that A has a unit, so that this formula makes good sense.
I mean, it can always unitarize, you know, if need be.
Yeah, sure, you can also do that. Yes. But as we will see later, there will be already enough technical complications for a unital A that I don't want to have excessive generality just yet.
Isn't that right?
Yeah. So this gives us the universal calculus. And then, as indicated here on the bottom part of the slide, there's a nice theorem of Kunz and Quillen that, again, in purely algebraic setups, characterizes projectivity of modules. And that can be characterized as stated in this theorem. So a right module X over A is projective if and only if it admits a universal connection. So that's a very nice result. And these two things settle in algebra the question of can we find a calculus, and can we find connections, or when can we find connections? And of course, we like projective modules because they relate to K-theory if they're finitely generated. So this puts us in a nice algebraic setup. So then the Chern character, well, recall that the K group of an algebra can be very quickly defined here on the second line. So it's the group of formal differences of isomorphism classes of finitely generated projective A modules, right modules. And this may seem somewhat unusual, and you can do things more generally. But now on this slide, let's, for simplicity, assumes that all A is also commutative and unital. And then this non-commutative de Rham homology is the homology of the universal differential graded algebra. And the Chern character can be then defined by this Chern wild type formula, where you take the trace of the exponential of the curvature. And then you show that on the level of equivalence classes, this does not depend on the choice of connection. It only depends on the projective module. And you see that this is computational. If you have a nice connection on your module, you can get access to the Chern character in this way. Of course, the general Chern character is defined for indeed non-unital, non-commutative algebras, and takes values in various flavors of cyclic homology. That all looks slightly different, but this is the underlying idea, is that connections allow you to get this information, to get characteristic classes, if you will, of a projective module. And so mapping K-theory to homology.
And what you compute does not depend on the choice of a connection.
Exactly. So that's what I said in words. So this is a well-defined map that only depends on the isomorphism class of this module P. And if you
actually stable isomorphism class.
Yeah, the K-theory class, really. Yeah. So, and then if you choose a different connection, you will get homologous cycles. So this is the nice algebraic setup, and now we're gonna go to another corner of non-commutative geometry, which is the area that studies spectral triples. So let's have a look at that. Also a familiar object for a lot of you, I think. So spectral triple, AHD, and here A is still my complex star algebra. So for some of the things that will appear later, it is vital that my spectral triple is graded. So I'm assuming that I have a Z2 graded Hilbert space here. Ooh. And this has to do with the important role that graded commutators with the operator in the spectral triple will play later. For simplicity, so this is a grading that I really need, that is vital to the construction. Of course, if you do very general KK theory, algebras can also be graded, and but this we can, for simplicity, forget about. So we assume that A has no grading and that it acts by even operators and possibly also faithful. So we don't want to divide out by kernels. And then there is the third point. So operator D, this is odd for the grading. So it flips the two pieces of our Hilbert space, and it's densely defined, self-adjoint, and it will have compact resolvent. So I'm assuming that I'm working with a unital algebra. On the other hand, I think it's also important to comment that actually the compact resolvent in this talk, and in anything I will say, will not play any role, really. There was a typo on the slide as well.
Where's the typo? Resolvent, okay.
Yeah, there was an L missing. I quickly put it in, you didn't even notice. And then the fourth axiom here is that the elements of my algebra, curly A, and so here it's important that I prefixed my algebra so that I will not assume that it's a C-star algebra, but more something like a smooth or differentiable functions, so that A preserves the domain in this representation, and the commutators of D and A extend to operators that are bounded on H. And then there are many commutative and non-commutative examples. The motivating example is that of a compact Riemannian manifold, where you take the Hodge-de-Ram operator on forms. So that's written out here. Of course, a lot of you will be familiar with spin manifolds or spin C manifolds, where you get nice Dirac operators acting on spinor bundles. So these are slightly smaller bundles than this full exterior algebra bundle. But the point of giving this example is that spin structure is really, or a spin C structure is not necessary to get a spectral triple. You can always get to this spectral triple. And then the other important point is that in such geometric spectral triples, these commutators, they are closely related to the differential structure, because this spectral triple arises from what is called a Clifford module, and the commutator of d plus d star with a differentiable function f will be equal to the Clifford multiplication of the by the one form df. So here we really see that the calculus on M is represented, or is hidden, if you will, in this spectral triple. So this means that one forms of functions are expressible as such commutators, and that is one of the cornerstone ideas behind Kahn's proposal of studying spectral triples as non-commutative manifolds. So abstractly, we can just take that at face value and say, okay, given that we have a spectral triple, we then get for free a module of one forms. Here, this omega 1d, which is, for me, the closure, that's what the overline bar denotes, of all such elementary one forms and their sums. And this turns out to be a bimodule over the algebra. So from one side, that is of course clear. So from the so multiplying by something in A from this side is of course clearly stabilizing omega 1. But if you multiply from the other side, you play around with the Leibniz rule, you see that you still remain in omega 1. And so this is a bimodule, but it sits inside B of H. That's where it's where it has arisen from our spectral triple data. And then there is a derivation delta D from A into omega 1, and that is just this commutator. And as you see from the previous Riemannian manifold example, this should play, or this should be really the representation of the one forms.
Sorry, may I have a question?
Yes.
So you are saying that in the classical case, this omega d1 would correspond to the one forms, but I have a problem with the closure.
Okay.
So what would be it exactly? The coefficient could be in general a continuous function, yes?
Yeah. The pre-coefficient, so the AI zeros here, you would allow for that. Of course, the strict one forms will be smaller, but for technical analytic reasons that become apparent later, I want to take this closure. And classically, you could do this too. So you allow slightly more general coefficients.
Okay, but would it be true that it would be just the same as all of this combination where as you said, pre-coefficient would be just continuous function? No, you still would get something bigger. I'm not so sure.
I am also not quite, I think even if you take the closure as from the left, it would be a function over a module over continuous functions. From the right, it would not. So I'm not able to give you a completely classical description here.
Okay, but nevertheless, we take a closure for some purposes, and we don't care what would be.
Well, if you take the one forms, classically, then that is some finitely generated projective module over C infinity of M, say, or over C1 of M. And so there is an inner product with values in these differentiable functions, and this thing would just be the C star module closure of that thing.
Okay, thank you.
So in that sense, it is a slightly more topological object. I mean, this is a fair point. All right, we go on now with this data. We have a module of 1 forms that is naturally given to us when we have a spectral triple, and we can then consider 2 things. So here I write omega hat n of d, and that by that I mean the n-fold tensor product over, say, the curly A of this omega 1d with itself. And I also want to consider the omega nd without the hat, and these are just the closure of what you would naturally think of as the represented n forms. And these are 2 different things, of course, because the first one has tensor products in it, the second one has operator products. Nevertheless, this derivation map that we have gives us maps between the module of universal forms. We can get into the omega n hat over here, and then using the multiplication map, applying multiplication in the bounded operators, we get a map to omega n as defined up there. And this is just some notation. This pi d is m composed with pi d hat. And these assemble into algebra maps, so you can use the tensor product as an algebra product, and then these universally defined maps are compatible with that. But they're not compatible with the differential graded algebra structure. As you may have noticed, I have not even given you one on these 2 new objects. In particular, I have not given you one on omega star of d. And the reason I didn't do this is because in general, there is none. So this is the first main problem that we run into when we work with the spectral triple. And I want to again emphasize that this problem arises when you take this sort of axiomatic viewpoint as proposed by Kohn, that the spectral triple should be really the manifold type object that you have. So everything should arise somehow from that.
So Bram, just a silly question.
Yeah.
What exactly is this omega star? Star stands just for arbitrary degree?
Yeah, so I think, did I say something about that over here? Yeah, I didn't write this again, but by that yes. I just mean the direct sum of all degrees.
Sure, I just forgot. Yes, you wrote it.
Yeah, no. I mean, I wrote it for the universal one. I didn't wrote this for the.
Yeah, but one can guess it. I mean.
Yeah.
Because it's confusing. You use the hot star, you have this star, and you have star in a star algebra. So
yeah, a lot of notation. No, so this is just the thing put together with all degrees.
Okay, I've got you. Yeah, just double check.
Okay, so as I already indicated, there's a problem with this represented differential. A goes to dA, and the problem arises when you have a universal form. Then it could be that this universal form is in the kernel of the represented form map, while its differential is not. And this is due to the identity that is written here, which at the moment is just formal. Use red. So the problem to get a map from differential graded algebras is that if you have a universal form, this could happen. And why can that happen? Well, because your differential in the represented world would preferably be taking commutator with D. But as you see, the image of, so this is like dA0, dA1, that thing. And this is what happens. And whereas this is taking the commutator, well, it's already written there. I'm not going to write it again, actually. So there is this error term involving d squared. Now, as I emphasized, this is a formal identity because I don't even know if the commutator with d squared makes sense. It's an unbounded operator. So, but formally, this is illustrating the problem. And here, the grading issues become important. So, because we work with graded commutators, these things are the same. So that is an identity that is always hidden in the background here, the one I've written in red just now. So another way of formulating it is that even if you would have taken care of the domain of this graded commutator, then clearly the map delta d, meaning taking commutator with d, does not square to 0. And in fact, it doesn't even map into bounded operators for even when restricted to 1 forms. So these problems, this shows you that there are a lot of problems with trying to just get some nice differential calculus from a spectral triple. It just doesn't work nicely. And this gives rise to the notion of junk forms, a term coined by Con and sort of stuck. So the junk forms are really a clearly defined notion, and they are really these things that are represented images of differentials of universal forms that are actually in the kernel of the representation. And so these are bad forms. Classically, what you see on a manifold, the junk forms in degree 2, they arise from the Clifford relations. I don't have this example spelled out at the moment, but in the classical case, you can get sums of products of forms like this, and this will, because of this should be an F. Because of the Clifford relations, this is actually a function related to just the scalar product on. No, this should be df dg. So this is related to the Riemannian inner product on the cotangent bundle, which is not a 2 form; it's just a function. So you don't want this to be in your 2 forms, and it turns out that in the classical case, the 2 junk is exactly of this form. So you can define this junk, and it is in that sense algebraically nice that they define bimodules. So the junk modules, as I've written here, either with or without a hat, they are bimodules. And so Con proposed to quotient them out, and if you do that, you get a differential graded algebra. So this is a way to get from a spectral triple a differential graded algebra. What do? You get rid of your junk, which is what the name suggests you would want to do with it. Now, in this talk, I'm going to take a different route and keep the junk. And the reason I want to do that is that the Con calculus, which is a nice calculus for many reasons, so I'm certainly not arguing against it, but what it doesn't do is it does not admit a representation anymore on B of H, because we've quotiented out some ideal in the differential graded algebra, we've made it. It's not a differential graded algebra. We've quotiented out some ideal of an object that was represented, and so we simply cannot represent it on B of H anymore. And that's the central question that this talk will be about: is can we define curvature for modules over spectral triple operatorially? So can we realize curvature related tensors actually as operators on B of H. And as I've argued here for you, there is no representative differential calculus. So we should just let go of that and work with what we do have.
Wait, let me understand. So if you look at omega star D before dividing out the junk forms, so is this representable in B of H or not?
Let me just slide back because I understand that there are many definitions, but the omega star of D is this thing. So that's defined to be represented.
Okay, of course, yes, of course. As a subset, yes, of course, yes.
This is really the algebra generated by omega 1 of D.
Of course, in B of H, yes.
Yes. So that sits in B of H naturally, but it's simply not the right thing, as Con understood. And because you cannot do your differential graded algebra business with it. So you have to divide stuff out, but then you lose the representation. So that's the trade-off.
But why do you use this representability? I just don't have an intuition. Why you lose it?
Well, if you quotient out an ideal,
yes.
So it's like, think of the Kalkin algebra, for example.
Okay.
If you have a Hilbert space, you have B of H, you have K of H, you divide out K of H, you get a Kalkin algebra, but that Kalkin algebra cannot be represented on the original Hilbert space you were working on.
Okay, so the question on the original. So how do you know that this cannot be represented on some other Hilbert space?
Oh, this I don't know, of course. But again, I'm taking the viewpoint that my data is AHD, and that in practice I usually know something about. So that's something I can work with. I mean, I'm not at all excluding that this can be represented on some other Hilbert space, and it might actually. I mean, if it's some operator space or C-star algebra, it will very likely have some representation, but you need to understand the Hilbert space you're representing on. This I haven't thought about. Maybe that's another route one could take.
Okay, thank you for the clarification. I mean, you wrote it correctly. It does not need a representation in B of H, where H is fixed. So okay. Yes.
So in our original Hilbert space, so that's what I'm focusing on. I don't want to get too far removed from the starting point.
Sorry, I'm a little bit confused since up to the dimension there is only one Hilbert space. Yes. So if you are saying that it maybe cannot be represented on H, you mean that maybe it could be represented on some different space, but this different space would necessarily have the bigger dimension. Yes, that's what you mean.
No, I don't mean that, but I mean this is the danger with the mantra that all Hilbert spaces are the same. I mean, all separable Hilbert spaces are isomorphic, but do you know and understand the isomorphism? If I give you two, you have to choose a basis, right?
Yes.
Yeah, this is not so easy to do, and certainly not.
So maybe
not a canonical operation.
So maybe the right way to think about it is that somehow the structure is richer, and then this item would spoil the structure.
The way I'm thinking about it is, so again, go back to the manifold case. There you're working on something like L2 of M or L2 of some bundle, and your representation is given by multiplication by functions or one forms. This is all very specific, and you can compute with it. If you represent on some other abstract object, then you would first have to find an isomorphism, and this all becomes very unwieldy in practice. When you try to compute some invariance, for example, you would like to keep track of the nice geometry that gave you these representations, right?
I see. So not only you are interested in the possibility of representing, but also you would like your representation to be somehow natural and allowing for some
So if I could find a natural representation of this con calculus that I could work with, then I would have nothing against it. But preferably I would like it to be related to H. So my starting data is really this spectral triple, and that's what I would like to keep working with somehow.
Okay, thank you.
May I comment this problem? So the problem is not about.
Can you show yourself, Tomek? Show yourself, please.
Wait a moment. Hold a moment. Let me do this. I'm not sure if you can see me.
Yeah, I can see you now.
Yeah.
Okay, so the problem is not so that we don't have the representation on the same Hilbert space, because if we had such a representation, there is not guarantee that this representation lists to the given representations omega star D.
Yeah.
Yeah.
Exactly. Yeah. So yes, that's what I mean.
Listing even if it there was such a representation of this quotient, there is not guarantee that it lists to the original one.
There's no guarantee that it bears any relation to the original one. Yeah.
Yeah, but even if there is any.
Yeah. No, you want this to be specific, indeed. You want it to be related to the structure that was given to you. Yes.
Yeah, very good comment. Thank you.
All right. So I indicated before, so here we have all this junk, but here also there was this formula that involved a d squared and a commutator with that. And I warned you that this was a formal identity. So to get around this not having a calculus, or not another calculus that we can work with, we need first to define a notion of what it means for a spectral triple to be C2. So that's this definition over here. And so that should have something to do with d squared. In the original axioms of a spectral triple, you only have a C1 type structure. But it turns out that the natural C2 condition is the following. We want the algebra elements to map some core for d squared into d squared. So you might as well think just about this, if that makes it any easier. And then we want to say something about the commutator. Now it turns out that it's not realistic to require the commutator with d squared and algebra elements to be bounded. This doesn't happen in the manifold examples. These will usually be first order operators. So I'm commuting a function with a second order operator. In the classical geometric setup, this gives me an order drop of 1, but that still leaves me with an order 1 operator. So the right condition, the right C2 condition is this one, that the commutators with d squared and functions are unbounded, but as unbounded as d was. And this condition is related to the more well-studied regularity axioms that exist for spectral triples, but these require much more than I need. So the reason for giving this definition is that I want to be minimal in my conditions, and this is the condition that we need. In a regular spectral triple, this kind of operator will be bounded, but you have much more requirements there. So you allow, or you require commutators of the algebra with the absolute value of d of arbitrary degree to be bounded there, and this is more than I need. So that's the reason for defining this. And on the manifold, this is what happens if you square d and you commute with f, then it turns out that this is bounded. So, and this is actually a workable axiom. So let's continue. Okay, these are some technical formulas here. The reason that I have those is that I need to at some point consider, or I mean, in the background of this work is some functional analysis, and so we need to take some completions, and we need to use some topologies. So here, given a C2 spectral triple, we can get two representations of our algebra, and the first one actually exists for any spectral triple. So because the commutator with D satisfies the Leibniz rule, if I put things in a matrix like this, I actually get something that is multiplicative. So if I multiply two matrices of this form, it will be again of this form. So what I mean to say is, if I carry out this multiplication, you can just do it, then you get this. So this is really a representation of the algebra. The only thing it's not compatible with is with the star structure, of course, because if I take the adjoint of this matrix, then the lower diagonal entry flips up. But this can be overcome in the sense that this is some defect that doesn't bother us. And for the same reason, this row 2 here looks slightly more complicated. But it's also an algebra representation that is not compatible with the star. You can check this for yourself. Actually noticed that here I should have written something different. So I want this for all I less than k. Sorry about that. So of course, for my C2 norm, I want both the C2 and the C1 norms to be bounded. But basically what I'm doing is I have a collection of algebra representations and I complete my algebra in such a way that these representations remain defined. And the reason I'm doing it in this way, so you will more often in the literature see things like this kind of norm. This norm here is equivalent to the norm given by row 1. This can be also quite easily established. The technical reason that I want to work with row 1 and row 2 is that these are so-called operator space representations. I will not go deeply into that, but again, these representations realize my differential objects as operators on Hilbert spaces that I understand algebraically from my data. And the reason to use operator spaces is the following lemma, that the multiplication maps that you get, and of course I use algebras of different degrees, so if I work with A1 and A2, then I multiply into A1, because what I have is A2 sits in A1, sits in A0, which is convenient to assume to be the C star completion of A. And I will not say what this is, but there is a completed tensor product that is nicely compatible with this algebraic structure, and that's the Hagerup tensor product. So there is a way to complete the tensor product so that the multiplication map remains continuous and well-defined. So that is really the reason for using these operator space topologies. But if you are not familiar with that, you can from now on more or less forget about them. And each time you see this tensor H symbol, you think, okay, that's the right completed tensor product. So now we use that to define forms. And as you see, this slide is called a poor man's C2 calculus. And that's because I am not going to get a full calculus, and I'm going to really have to work with my hand and feet here. So I'm going to define one forms as being the kernel of a multiplication map like this, but I want to again be able to work with either my A0 and A1 or A1 and A2 together, and then end up in their lowest part. And the two forms, I am just going to make this mixed tensor product where I allow, as related to the previous question, somehow continuous coefficients, but differentiable entries in my forms. And this is an approximation of a calculus in the sense that, okay, the differentials are defined because they're universal. All I've done here, this is like the lowest part of the universal calculus made somewhat analytic. So I've used the completed tensor product, but I also need to use functions of different regularity. So C0, Z1, C2. And this is just to give me maximal flexibility.
There's a question.
Yes.
I have a question about this balanced Hager product.
Mhm.
So you are raising. You are transforming these objects into matrices of these objects, and you are doing this for these two modules, which are tensored, and you have to do this with A1, I suppose.
You have to balance, yeah. So the way you do it is you first form the.
I'm not familiar with the balanced Hager tensor product.
So
I'm trying to discover what it could be.
Yes. So what it is quickly is that you take first the usual Hager tensor product without balancing, and then you take the subspace generated by the balancing tensors, and you close that up and you quotient it out. So you have some Banach space. It's in this case an operator space, and you quotient out a closed.
So this is not a completion of the Hager completion.
This is a priori.
Product.
This
Okay.
is a priori unclear. Yes, this is what.
It's a quotient. Okay.
Yeah, it's a quotient of the unbalanced.
Now I understand. Thank you.
This is, I think, Blecher and Lemerdy in their book on operator spaces. They describe this procedure in some detail. So the lemma here on the middle of the slide should convince you that working with these mixed forms is a good thing, because I can now make rigorous some things I said before. First of all, about commutators with d squared, and secondly, I can understand once I represent my completed spaces of analytic forms, what kind of mapping properties they have with respect to D. And it turns out that these one forms, if I take the coefficients in A1 and A2 like this, then I get operators that preserve the domain of D, but that are also bounded for the graph norm. So I'm writing here the bounded operators on the domain. Domain of D is a Hilbert space on its own, equipped with the graph norm. So this tells me that these represented forms preserve the domain and do so in a controlled way. And I can also induce my universal forms using the commutator with d squared, which does not land in bounded operators on H, but it turns out that it lands in bounded operators from the domain of D into H, where again, the norm on this operator space is defined using the graph norm. And this also gives you a neat description of the two-junk, because it turns out that the two-junk is exactly the closure of pi d squared applied to pi of D. This is a result we will not really need, but it's a neat consequence of the setup. And yeah, as commented below the lemma, this identity of the junk module follows from this algebraic identity, which is now a rigorous thing. This is not an identity of bounded operators, but it's a specific identity of unbounded operators that can be safely worked with. And we can also now define what we mean by omega 1 of d squared, which is a subspace like this, which it should be, but now we want to view this as operators on the domain of D, which can be done by virtue of this lemma. So again, what I want to achieve with the setup is that I can safely do my algebraic manipulations in an analytic context.
Sorry, is B1.
Sorry, can you repeat what the BIs are? B1.
The same question.
Huh?
Can you repeat what the BIs are? B1, B2?
B1.
Oh, B's are, oh wait, there's a B that appeared. This should be an A. I don't know if that's what creates the confusion, but this should be just an A. And
So it is a typo. Okay.
yeah, sorry, the B, this may happen again. I apologize for that. I often use B for this type of algebra. So when I was writing the slides, this sometimes happened to me. And this one I hadn't spotted yet, so thank you. So I'll correct it afterwards when I make the slides available. But no, so it's just A0, A1, A2 are the respective completions from the spectral triple. The B's should be ignored, or they should be A's really. All right. Now two connections. So we work with a C2 spectral triple, and another typo here, X some right module over, well, either A0, A1, or A2. And then we say that this module is CK if it admits an inner product in which it is a pre-C star module. So I want the axioms of a C star module, which I will not list here, including the positivity axiom for the enveloping C star algebra. So you could also say we have a C star module which with a nice submodule whose inner product lands in the right algebra. And this is a very weak differentiability condition on the module. And then we want to work with connections, and now the next subtlety presents itself. So a connection will be such a map where you see that the target is a completed tensor product. This is the flexibility one needs. Of course, there is the usual Leibniz rule. And when you have such a connection, you can construct the completion of the module, initial module X.
And sorry, what is the straight X?
So this straight X, this I should have written in the definition, is the C star completion of the curly X. Because I'm assuming that curly X is a pre-C star module over this subalgebra, so I can always close it up to get a C star module. And that's the same with the straight A. So the straight A means the C star closure of the curly A's.
Okay, thank you.
Sorry, don't you require this X for this Hager tensor product to be defined to be an operator space?
Yes, but any C star module is an operator space.
Ah, so we identify this. Okay.
Yes, well, it turns out that every C star module has a natural operator space structure coming from embedding it in its linking algebra.
Okay.
So I didn't want to go. These are all extremely.
Yeah, so this is a single column in this.
Yes. Yeah. Exactly. Yes.
Thank you.
So these are all extremely important analytic facts that play a role in the background here. But I didn't want to make this an analysis talk, so I wiped some of them under the rug. But these are very good points. This is what's happening here. And even this X nabla that I indicate here, this completion, this can also be done in such a way that X nabla is actually an operator space. And that's what you see on this line. That this is, you need to define what you mean by a connection to BC2. What I need to do is I need to first complete my module using the connection, and that tells me what the C1 submodule is. And then I say my connection is C2 if it actually restricts to a map from the curly X into this tensor product which features the C1 completion. And this is not circular. This is simply how one has to do it.
And could you elaborate, please, how you complete this curly X using a connection? Because I don't have any feeling about it.
What you again do a 2x2 matrix trick. So you view your C star modules as operators, and then you can form such a matrix. And let me show you what happens when I do this. So this is my representation of my C1 elements, right? I showed it to you before. And if I multiply this out, I get XA, then I get nabla XA here at the bottom. And you need to get your conventions right. So the multiplication here should be the tensor product. And here I get just XA. But my Leibniz rule now tells me that this is exactly that. So this is compatible with that algebra representation. And there are more algebraic structures that are compatible with this kind of representation, but this gives you a natural operator space structure on the domain curly X. But if you're interested in how this works, there is a paper by Bletcher, Kant, and myself in 2018 in the Proceedings of the London Mathematical Society, where this is all described in detail, how to do this.
Sorry, in fact, this idea goes back to Atiyah under the name of Atiyah extension and the connection as a splitting of the Atiyah extension.
Right. Okay. I did not know this. Well, I need to make a note of myself for that. Thanks. I will look that up. But this shows you that the connections are very natural to study in an operator space context, but that the philosophy is really that what is always going on is this lower triangular matrix trick. And that allows me to define what I mean by C2. So I want the map to restrict then to this completion, and there's again a Hagerup tensor product. And why do I want that? Well, because then the composition nabla squared is actually defined. One can then also check, and algebraically this works the same as in the universal algebraic calculus. And here, when you take the completions in this way, then you can actually show that this is a safe thing to do analytically as well. So such C2 connections have a curvature, because this map nabla squared written here is also A2 linear. So it has the same properties. I also want to emphasize that this completion here, this X nabla completion, I will comment on this case later, but if you're a finitely generated projective module, then there is a more canonical way of doing this, because then all connections are bounded perturbations of each other, and it doesn't really matter which one you use. You always get the same completion. The reason for this extra care is that I want to cover infinitely generated modules as well. And then it turns out that what is central to the analytic instructions is the connection, and not so much the generators of the module or something. This is just seems to be just a fact of life. So another thing we can do with these connections, so we have now a C2 connections, and it has some curvature, but this curvature still lives in the universal realm. Of course, we can represent it using the maps I showed you before, and we will actually do that. But we can also do something else with these connections. Namely, we can represent them in this way, where we can use both the induction maps from D and from D squared. And of course, the ones from D squared only play a technical role. They don't really have an interpretation as forms. That I showed you, when you deal with two forms, this D squared becomes important. And when you have these represented connections, you can form induced operators. And this is a construction that also, I think, goes back to Kohn in the finitely generated projective case, where what you need to do is, when you want to induce an operator to a balanced tensor product, you have to account for the fact that this kind of expression is simply not well defined with the balancing. So if you put the A on the X or on the H, because D doesn't commute with the algebra, that term is not well defined. But if you add a connection term like this, or in this case like this, then the error gets compensated for by the Leibniz rule, and these become well-defined operators. That's again something you can check algebraically. And if the connection is Hermitian, which means it satisfies this here.
Bram, do you agree that you have a missing? Yes, okay. Parenthesis, yes.
Yeah.
Okay.
Yeah, I will do several typo corrections after this. So this is the Hermitian law, also familiar from algebraic setups. And if you have that, then you can check that this that these operators, these induced operators, are actually symmetric. I am deliberately not saying anything about self-adjointness here because that doesn't come for free. You need some extra axioms on your module, which I will not bother you with. But also, maybe the good news is that for this talk, we don't need that. But it's good to be aware that such induced operators, when you use an infinitely generated module, they are not automatically self-adjoint. And actually, we know of examples where they are not. So there's care to be taken here. But if the module is, for example, finitely generated, there is no problem. Then these lifts will be essentially self-adjoint. So we can form these operators, and we can show from our mapping properties and things that this subspace, which is an algebraic tensor product, I've not completed anything, is actually turns out to be a subspace of the domain of the square of one tensor nabla D of the induced operator. So this is again not obvious, but this turns out to work out as a nice combination of algebra and analysis. And this means that the difference, here's another typo, is defined. We need the domain of D squared there on that space, because that space is a subspace. Well, the second operator here is just defined on that subspace, and the previous lemma shows that the first one is also defined there. So this difference is a well-defined and symmetric operator when you have a nice C2 connection on the module. And of course, that difference measures the fact to what extent this operation, the one tensor nabla operation, or the lifting of operators from H to the tensor product with X, fails to commute with taking squares. And in the spectral triple philosophy, the square of a Dirac operator is approximately the Laplacian of your underlying geometry, modulo some curvature terms. And so this difference in the corollary should be viewed as a difference of Laplacians, where you have the Laplacian of the lift and the lift of the Laplacian, and you compare them. Now, as I said before, the composition of nabla with itself is well defined, and it's an A2 module map, so we can represent it, where I use the shorthand pi d of nabla squared for its whole composition. So we first take nabla square in the line here, then we see that one tensor pi d is defined on this tensor product here. And once we've represented that, we want to get back to our original Hilbert space, so we multiply it out. So what I mean by pi d nabla square is just a natural representation of this thing on our original Hilbert space. And then it turns out that the following theorem at the bottom is actually true, that the represented curvature of this connection is exactly equal to this difference of Laplacians, which I find still quite remarkable. So that's, if you will, a new interpretation of the curvature of a module, is that it can be seen as this this defect in the lifting of the Laplacian associated to the spectral triple. So that clears up this thing. So bottom line is, okay, you need to do some analytic work to make everything operatorially well defined. You need to accept that you don't have a real calculus, but then you get this result. All right. Now, this brings us, of course, to this definition that the curvature operator of a C2 connection is simply this operator, which now has two appearances, difference of Laplacians, or simply the representation of nabla squared. And now you can wonder, because this uses universality. So when we started this project, we were really hoping that we would not have to refer in any way to universal forms, but could do everything in the representation directly, which is, we haven't succeeded at that. We need somehow a place where we can apply the connection or the differential twice, and in the most generality, you don't have this unless you go to universal forms. But we could also show that, okay, suppose that so again, in practice, when you're doing geometry, you have access to nabla D, so the represented form of the connection. And connections are generally not given to you in the universal calculus. So you have to work to lift them. And this is also what we really had to do when we wanted to do computations on Riemannian submersions, that's where we had to actually work to lift our given connection to a universal one. And it was not so easy. But you can wonder, okay, what if I find two different universal lifts? So that's what this condition here means. Suppose that I have nabla and a nabla tilde that are universal connections, but that representatively give you the same connection. Well, then it turns out that this represented curvature only sees junk in a very precise way. So there are the junk forms again. But so this curvature operator is well defined up to junk, which it should be given the existence of Kahn's universal calculus. Now, another example is that of free modules, and free modules are usually thought of as direct sums of the algebra with itself, either finitely many or countably many times, but you can also think of them as tensor products over the complex numbers now with just some vector space. And then you have basically the differential itself, as written here, is a connection, and it's a connection of zero curvature because d squared is 0. And so from that you deduce, but this you can also prove directly, but deduce from these results that, okay, the curvature is 0, so the Laplace lifts, the two ways of doing that, they will coincide. That's not surprising, because if you compute what these lifts are, then in the free module picture, they are just diagonal matrices, both of them. So there's no curvature and they're the same. If I now take an arbitrary connection on this type of free module, so this means that I could add some one form, then this result shows that if you compute the curvature operator of an arbitrary connection, then it will always be junk. That's what this implies, because this, as we know, the difference of two connections is just given by multiplication by forms. So if we compute the curvature for this one, and this says C star, it needs to be C2.
Yeah.
So that is something you can derive, and it also corresponds to the fact that, okay, trivial bundles should have no essential curvature. So in K theory, they shouldn't carry any curvature information. Okay, now the general finitely generated projective module case. In this setting, where we have inner products. So we are working with pre-Caesar algebras after all, and projectivity will mean that we can choose some isometry, so some inner product preserving map from X into n copies of my algebra A2. And then you can construct a frame by just pulling back the standard basis through this isometry. You could also start from a frame. Any projective module, any finite projective module admits such a frame. So a frame is a finite set satisfying that any X can be written as a sum in these generators. So this is a generalization of a basis. And of course, these things are not orthogonal. And then you can make a Grassmann connection, as is written here, either using the frame directly or using the isometry V. And so that is a way to show that an FGP, a finitely generated projective module, always admits a connection, is to say, okay, frames are always exist. And once I have a frame, I can pull back the trivial connection on the free module through this isometry. But that also means that I can compare an arbitrary connection to such a Grassmann connection. And then we can derive a familiar formula in curvature land. So if we have a nice C2 connection and we choose some isometry, then we get a connection form, this AX over here, which is by definition the difference of nabla and nabla V. And then if you compute what the represented curvature is, it gives you exactly, or it gives you something that looks formally very similar to the formulas that you see in principal bundle theory, for example. So you really get something of the form P dP dP plus A squared plus dA, where I've written the last equality in quotation marks, because what you really get is of course the second line. So
sorry, Bram, if you don't mind, just a very quick small comment. Yes, of course, having this frame and the recipe for a Grassmann connection shows you that every finite generated projective module admits a connection, but in fact, for the universal calculus, projectivity of a module and existence of a connection are tantamount.
yeah, I mentioned this in the beginning, right?
Okay, sorry, I forgot. Yeah,
the Kuhn-Quillen theorem, and that you don't need the finitely generatedness.
Yeah, you don't need it. Yes. Yeah. Sorry, I forgot it.
But it's a theorem in pure algebra, of course. So, but yes, that's the same. So, but this is just a way to do this. But this holds much more generally. But it's gratifying that we recover these formulas. All right, so this was sort of the most technical, detailed part of the talk, although it will not become any easier maybe, but I now want to expand the focus and go to correspondences, because the kind of curvature we're looking at is really a relative thing. So before we had spectral triple, I lose my, yeah, there it is again. So we have a spectral triple AHD, and we have some module, and basically what one is doing is constructing a new spectral triple type object. I'm not going to comment on what algebra I want to put there. But we lift these operators and and then compare them. And so this is a simple case of an unbounded Kasparov product, or a correspondence and between two spectral triples. So that's what this definition is about. Suppose I have two spectral triples, one over A and one over B, then a differential correspondence is a triple over here, X as nabla, and I'm being vaguer in this last part of the talk because it will become too much to list all the technical axioms, and I really just want to give you the idea. You should trust me that this works with the right analytic conditions, but the underlying structure is algebraic. So I can use this data. So X is a module, S is an possibly unbounded operator on this module, but it's a linear module operator. And nabla is a connection, and they need to satisfy some compatibility conditions. And when you have those, you can do this operation. So I can couple this data to the spectral triple, so X is now a bimodule for A and B. That's different from the previous setup. I didn't consider any left module structure. Then I can form this tensor product. That's again a Hilbert space because X will admit a C star module completion. So this is again all happening in the background. And then I can form this operator. The S tensor 1 is not problematic. And then I add the one tensor nabla D1, which I just explained to you what that is. And then you need to make sure that the sum is well defined. There are all kinds of technical things going on, but suppose that you have this setup, then that this works, and there are many examples of this. Then the spectral triples are linked by this triple XS nabla. And
what is S again? S is an operator from where to where? What is S?
S is an operator from X to X. And it's B-linear. It's a module operator. So, and in the C star completion, you should require that it's self-adjoint and regular and all that. So this is the kind of operator that features in unbounded KK theory. And this algebraic operation that I describe here corresponds after equivalence to the Kasparov product. This is really what that is. And then I want to require that the object that I form in this way, it resembles my other spectral triple, AH0D0. And it turns out that it's not reasonable to require that the operator D0, it will in general not be exactly equal to this product formula. There is some error terms, and they turn out to be also related to curvature, but to a different type of curvature than I'm talking about today. So there is something, but that something can be quantified, and that something does not influence the class of the operator, for example. And also, you need to do this up to unitary equivalence. And then using the same philosophy, namely this philosophy that this type of Kasparov product formula doesn't commute with squares, because it doesn't. And if you have this setup, you can do two things. You can square your product operator, and you can, well, take the terms. S squared tensor 1 is again unproblematic. One tensor nabla D1 squared is involved, but the first part of the talk was all about explaining you when you can actually do this. And then you can talk about the curvature of this correspondence, so the curvature of this object that goes between these two spectral triples. And I will give you some examples.
Sorry, Bram, I'm a bit confused. I remember that you used connection to complete your curly X.
Yeah.
But what do you mean by this connection completion of a tensor product?
Where is no, that's an operator. So this is just the notation for this induced operator. It's here in the middle of the page over here.
Oh, in the middle. Oh my goodness, yes, I forgot.
So this is just for single operator that I use this sub nabla symbol.
Mm-hmm.
So that doesn't mean any completion.
Okay, that's a bit confusing. Okay.
Yeah, it's just a single operator that I built using the connection. So you could also,
yeah, I know it's a single operator, but I thought that it indicates somehow the space on which it lives, and it does. But you use this nabla instead of A2 or whatever there was. It's balanced over.
yeah. That's just so. I think in some older texts you find some notation like this, which is really
Mhm.
what it is somehow. Well, that's also cryptic, so I don't know what's less confusing.
Okay,
Can
thank
I
you.
ask a question about this first definition?
Mhm.
So coming back to this first one, so this means that I wonder if you had this perspective in mind, writing this condition for the differential correspondence. So this spectral triple is regarded as a differential correspondence from A to C in a sense.
Yeah, it's mapped to a point.
Yeah, and then you have the commutative triangle of these three correspondences.
Yeah.
Mhm,
Yeah, so this can be put in a diagram indeed.
mhm, mhm.
And this excess nabla should be thought of as some morphism going between
Yes.
these two objects.
Okay, thank you.
And that's also how they arise in examples. But let me first, so we saw the example of the trivial connection on a free module. A similar thing happens here when I have an external product of spectral triples, then there is no curvature. And that again this combines the two viewpoints. So there's a way to form external product of spectral triples where you have to take graded tensor products so that the two legs anti-commute. And here there is no balancing in the tensor products. Then you can make a correspondence, namely this one, H0 tensor B, D0 tensor 1, and the little sub D, which just differentiates on the B leg. So this fits with the example of the free module as a tensor product with a vector space. That's what this module is. And this defines a correspondence between the external tensor product and the second spectral triple. Why is that? Well, if I have H0 tensor B and I take balanced tensor product over B with H1, then that is the same as the unbalanced tensor product of the Hilbert spaces. So the B just disappears from the setup. And so I can view this external tensor product as an internal tensor product in this way. And the connection operator that you get from this trivial connection under this correspondence just gives you the usual external tensor product operator. And then because the operators anti-commute, so the anti-commutator of these two things is 0, which amounts to this equality over here. And then if we go back to the definition of this curvature, then you see that it vanishes. And this fits with the perspective that this curvature is a relative notion, and that this tells us that the curvature of a direct product fibration, so I have two manifolds, I take a direct product, I project back to one manifold, should not be any relative curvature in this kind of fibration, because the fibration is a direct product.
You mean the Cartesian product?
That's what I mean by direct product. So I have two manifolds, and I think of this kind of situation. Maybe I should use 0 and 1 to be.
So you mean the trivial bundle? Trivial fibration.
Trivial fibration, really. That's the underlying topological setup here. Okay, now
what is the little d in the correspondence?
it's the exterior derivative, so it's really the universal. What's the algebra here? B, right? So it's the universal derivation that we've seen in the very beginning. And this is a connection because this module is just a vector space tensored with the algebra.
Yeah.
So that's the reason why that works. Well, these correspondences have been constructed in many settings. I don't really want to spend too much time on that, but these are all settings where you can study potentially the curvature. So now, just finalizing the talk without getting too technical, but so I showed you that trivial fibrations have no curvature. Of course, we know in Riemannian geometry of many nice non-trivial fibrations, such as the Hopf fibration, and that's a non-trivial fibration of spheres, to which you can also naturally assign such a correspondence in Kasparov theory. So we take the spin spectral triples on the 3-sphere and the 2-sphere, and by just using their Dirac operators. And it turns out that this fibration allows you to build some cycle coming from the Peter-Weil composition of S3 and also Fourier analysis on S1. So this module has many incarnations. I'm talking about the commutative version now, but this has also been studied for SUQ2 over S2Q and for theta deformations and so on. It always has the same structure. The module that you get from this fibration is a direct sum of sections of line bundles. Or
this is the algebraic direct sum over all integers, right?
Well, I mean, when I write the straight acts, yeah, this is over all integers. That is correct. And you can, as a C-star module, I want to complete it, but as a smooth submodule, it's safer to work with the algebraic direct sum if you want to look at the domain of the connection, for example.
Yeah, because this is precisely the Peter-Weil commodule algebra of this fibration.
Exactly. Yes. Yeah. So that's the thing that appears here. And then each of these line bundles has a natural connection, and you can put them together, and this gives you one of these correspondences that satisfies the axioms on the slides before, linking S3 to S2. And
sorry, what is this natural connection?
This is just the line bundle connection. I don't remember how you can just write it down. What is this again? This is the degree 1 and -1 modules are related to the tautological line bundle on S2, and then you can just write. There's a natural embedding in the rank 2 free module that you can take the Grassmann connection off. So you can.
Okay, so when you say canonical, you really mean Grassmann, and
well, Grassmann,
the kind of embedding you take.
Grassmann is relative to some embedding, and there is
sure, yes, yeah.
There is a natural embedding in a free module here because of the very nice geometry, and that's the one one takes, and then you get such a correspondence.
For n positive, you have a simple formula, but for n negative, this formula is more complicated.
I guess so. Yes.
So positive charge comes from this tautological
right
bundle, but for negative, it's more complicated.
But the connections are not dual somehow. The modules are dual. Yeah.
These are direct summons in more complicated modules.
Yeah,
I rank.
Look up the paper again.
Also, one of the reasons I'm confused is because if you look at it at the level of continuous functions, but you can always have it in a rank 2 module, free module.
Yeah.
But if you want to do it algebraically, then you have to grow the size of your free module in order to embed it. So for me, it's a bit of an overstatement to say natural, because it depends on your point of view. I mean, it's
yeah, sure. So I think what we did was we actually put together. So if you put together the positive and the negative, then you can.
Oh yeah, surely, because when you add ln to l minus n, this should be a free module. And so we are doing it over complex, over continuous functions. Okay, okay,
Yeah.
I got it. Yes.
So I think that's the one we used, but I must
Okay.
admit that I would have to look in our paper again.
Yes.
It's a while
No,
ago.
I'm just trying to fix your point of view because surely you shouldn't write canonical here. This is definitely way too strong. I mean, you have a nice Grassmann connection, and then indeed here, because the topology is so natural, you can exactly as you said, you can add Ln to L minus n, and it will be a free module.
Yeah.
And that's very natural. And then this gives you an embedding, and then it gives you a connection. Okay, I've got you now. Yes. Yeah.
Okay.
So
Well,
maybe canonical in this context means that it is given by obvious formulas coming from classical geometry.
yes, this is
But I
what
would
it
say
means.
it's canonical.
And it also, yeah, the word canonical is always up for debate, of course, in
It
many.
is some choice, for instance, the scalar product in this
Yeah.
ambient.
No, of
trivial
course, it
quantum.
involves many choices, and the choices should be made such that this is true. So we want this relation between the two Dirac operators, which in this case is this S tensor 1 plus 1 tensor nabla T. So that also forces what you have to choose for the nabla N somehow. And then you have this error term of 1/2, which is related to the intrinsic curvature of the Hopf vibration. But the point, maybe it will always be seen, I guess, when you, because these line bundles, they have increasing Chern numbers. And so what you will always see, whatever sequence of connection you choose here, is that because this was another point I wanted to emphasize, we have here a fibration of compact manifolds, but the module X that we get is infinitely generated.
Yes.
So that's why the whole careful discussion of the first part of this talk is relevant in such a context already. And the total curvature operator is also an unbounded operator. So the curvature on a finitely generated projective module, so on each of these line bundles, the curvature will be a bounded operator. But when I put them all together, this will be an unbounded operator proportional to this multiplication by n operator, because each of these curvatures reflects the Chern number, which is n, and this operator grows like that. And this is what you actually see in general submersions on between compact manifolds, that this curvature operator is always some unbounded operator, but its unboundedness is related to this vertical operator that also appears in the correspondence. So
May I ask a question about this, let's say, total curvature? So if you think about the Riemannian submersion, then you have a canonical choice of a connection in the sense of fibrations, which is the orthogonal complement to the fibers.
Yeah.
Okay. So my impression is that this total curvature of all these n's should correspond to this curvature of this Riemannian submersion, in a sense.
Yeah, I think that is true. So I was gonna give you the general.
So unboundedness is not important then, because it's not a linear connection. It's a connection on an algebra, in a sense. So finite, so boundedness in the sense of linear maps doesn't play a role here.
What do you mean by that? I'm trying to understand.
Because instead of linear generators, you have algebra generators. And there are some relations between them.
Yeah.
At least classically.
Right.
Okay. And then this n is a consequence of algebraic relations between algebra generators.
I see.
So if you write everything in terms of algebras and the curvature is meant in the sense of this Riemannian submersion, there is no a problem of representing this on the Hilbert space and regard this as a linear curvature of a module of infinite rank.
Right. Okay.
Because it's, in a sense, it's finite as an algebra, although as a module, it's infinite, of infinite rank.
Yeah, it's of infinite rank over the base.
But as an algebra, it's finitely generated, because you have a finite number of generators and relations.
Yeah, like on S3 itself, right?
Yes, precisely.
Yeah.
By the way, Bram, since some people are already leaving, you have -6 minutes left.
Yeah, I
So
was.
you should speak faster than the speed of light to get us back on path.
Right. Well, I have 3 slides left, one of which says thank you.
Okay.
So let me just we can go over this quickly because we've discussed the previous example. So for a general submersion, as Tomek was commenting, Kaat and von Seilekom proved that there is a factorization. So there is also one of these correspondences, and you can apply this curvature theory there. So the first curvature term you pick up is this Clifford multiplication by the curvature of the submersion. And then, okay, we computed the curvature operator as I defined it in this.
I'm sorry, but you have such a funny typo.
Yeah.
That's really.
This is terrible. Yeah. That is quite bad. I will also correct that one, of course, before sending the slides to you. So we could compute this curvature, and you see again that that natural curvature information arises when we compute our represented curvature, and this reduces to the case of the Hopf vibration as I just presented to you. So let me just leave it at that. Where the only thing I want to say is that the difficulty here was still that we had to work with this universal calculus, which we would very much like not to have to do. Okay, that was it. Just quickly summarizing curvature links geometry to topology. We have problems with differential calculi for spectral triple. Represented forms force you to look at junk, and then if you want to deal with analytic forms, you use operator space theory. And then the main result is that the curvature of a connection is the difference of certain Laplacians. This is really the central result. And then we could compute this in various cases, including Riemannian submersions. Of course, a very nice ultimate goal would be to get some bivariant Chern character in unbounded KK theory, but this seems to be still very far away. And that was it. Thank you very much.
Thank you very much, Rob. Okay, let's start questions. Tomek, you are just clapping. Adam already left. Anybody from Warsaw? No?
I would have a minor comment on
Yes.
your C2 condition.
Mm-hmm.
So it looks like in the classical situation of skew-symmetrized differential forms on a manifold, this C2 condition plays a role in the Schwarz theorem, saying that the second derivatives of a function of class C2 has symmetric second partial derivatives. The Hessian matrix is symmetric. So this means that after this skew symmetrization, you can kill this symmetric part.
Yeah.
Okay, and this means that the exterior derivative, the RAM differential, is well defined.
Yes.
So in a sense, your C2 condition somehow cancels this symmetric part of the second derivative defined in terms of the connection. So this is my understanding of this. Of course, of course, the symbol of this or this Laplacian, of course, it sits in the symmetrized part.
Yes.
So after killing this, you obtain something which classically purely is defined in terms of the skew-symmetric differential form.
Yeah. Okay, I see what you're saying now. Yes.
But you are doing something more. You are not symmetrizing this second derivative.
Yes. You remain in the Clifford representation, which is
Yes,
like,
you are in the Clifford representation, but you have a way to cancel this symmetrized part in a sense.
Yeah,
so
I
this is interesting. Yeah,
think that makes sense. Yeah, it is
because you need only to kill this Laplacian. You do not have to kill or symmetrized differential operators of order 2.
Yeah, exactly.
So it's a very, very good idea that everything reduces only to canceling only one such differential operator of order 2, which is the Laplacian.
Yes.
Very nice idea. I like it very much.
Well, thank you.
Thank you.
Thanks for this comment, because this is also useful. All right.
Anybody else? If not, I have an obvious question. Maybe it was just my wishful thinking, but I saw some Q floating around in your slides. So do you have some few examples of?
Oh, well, actually, that was probably the slide that I skipped over.
A non-example, okay.
So, as you know, fitting Q2 with the spectral triple paradigm has not been done. And so one would like to have one of these correspondences of SQ2 over S2Q, and at the moment there is none available really. So this is still a tantalizing non-example.
Yeah, but how about theta deformations? You have so many.
These are fine.
Okay.
These are very tame, of course, because the theta is on the unit circle or something. So the problem with the Q is that it's real.
Yeah. Okay, so let's thank our speaker again. Thank you so much. We were really very happy.
Well, it was my pleasure.
And thank you for giving such a technical talk, because you showed us the whole cooking, and I appreciate it. I mean, you didn't just serve us the meal, but I felt that you showed us how you cooked it. So,
well, thanks. Yeah, well, that's when you get such long speaking times, you can do. So,
yeah,
that was nice.
Sorry, before we end, could I ask one non-mathematical question?
But we are being recorded, so you should really don't ask anything political or immoral.
No. It's about the very beginning of the talk, because you said that the proto version of this talk was made in Krakow not so long ago.
Yeah, 6 weeks ago or something. Yeah.
Could you tell me whether or not it was some organized event or anything? Because both me and Adam are based in Krakow, and we had no idea anything connected to non-commutative geometry was happening since September.
Oh, but there was this conference, right? That's what I'm talking about.
Okay, well, let's discuss it after I stop recording. So I stop recording,